Hi everybody, this is Professor Stewart with a final video on calculations that we can do regarding stray light. So in my video on monochrometers, I talked about stray light and how it can affect the absorbance measurements that you have and cause errors. And so let's do a calculation where we say we have 1% stray light, and the amount of stray light we have is compared to P naught, so the amount of light we have, the signal we have when there is no absorbance, right? So when there's no sample in our instrument. And so let's look at two examples. So let's say if the true absorbance is equal to 0.1, what's the error that we would have if we have 1% stray light? So if we have a true absorbance of 0.1, let's calculate what is the transmittance. So if we remember, absorbance is equal to the negative log base 10 of the transmittance, and that's the same as the negative log of P over P naught, because we need to express this in terms of P naught to be able to get this to make any sense. So we can say that P over P naught is equal to 10 to the negative value of the absorbance. And so our actual transmittance, if we have an absorbance of 0.1, is 10 to the negative 0.1, which is equal to 0.794. And what we want to see is how does that transmittance compare to what the transmittance we would get if we have an extra 1% stray light, and that will show up in both P and P naught, because the stray light is not going to depend on the absorbance of the sample because it's at a different wavelength than where the sample absorbs. So we'll call this amount of stray light S, and we say that's 1%, which is equal to 0.01. So if we define P naught to be equal to 1, our S is going to be 0.01 relative to that value, so 1%. So our apparent transmittance is going to be whatever P is plus the amount of stray light we have over P naught plus the amount of stray light we have. So the stray light will affect both P and P naught in this calculation. And so we can say if our P naught is equal to 1, our P would be 0.794. And then we add our stray light to both of these. So we'll end up with 0.794 plus 0.01, and on the bottom one with 1 plus 0.01. So if we go ahead and calculate that, we get a value of 0.787. So there is a small difference there. And we can plug that transmittance value, that apparent transmittance, will give us what our apparent absorbance is. So that'll be negative log of the apparent transmittance, which is negative log of 0.787, and that gives an absorbance of 0.104. So it causes a small difference, and if we want to write that in terms of errors here, right, it's about a 4% error. Okay, so causes some error at low absorbance, but what we really want to see is how does this change if we go to high absorbance? So in my other video I said high absorbance would matter more, and let's go ahead and look at that. So let's say that our true absorbance is instead 2, which is sort of the highest range the highest range that you'd want to even measure with absorption spectroscopy. When you get to that sort of absorbance, it becomes much less reliable. But anyway, we'll kind of go into an extreme example here. So if the absorbance is 2, what is our transmittance? P over P naught is 10 to the negative absorbance, which is 10 to the negative 2, which is 0.01. Add some extra zeros here. Okay? And so this is our true transmittance. Our apparent transmittance is equal to, again, P plus our stray light and P naught plus our stray light. And we'll say that, again, we're calling P naught 1 just to make it the numbers work out. Everything's relative here. So we can call it 1 as long as we know that everything's relative to 1. So 1 plus 0.01 over 0.01 plus 0.01. And you can already see, right, that this is going to be a huge error because we've essentially doubled our value for P, even though the P naught doesn't change very much. And so that gives us a transmittance of 0.002. 0.0198 once we go ahead and calculate it, and you can see that that transmittance is significantly higher. So A is equal to negative log of T, which T apparent, right? So this is the apparent absorbance, is negative log of 0.0198, which is 1.70. And this is like a 15% error, a huge error. And so we can see at high absorbance values, the amount of stray light you have matters a lot. So if you want to measure very large absorbance values, you really have to have a monochromator that doesn't have hardly any stray light contribution, or else you end up with very large errors. And so you get a chance to practice this on your homework. You have a question like this. So hopefully this will be able to help you. Again, I'll upload this PDF for you to look over this.